All right. Afternoon, everyone. How is everybody after a long 3 days of getting information pumped into your heads? Everybody's still here, and you came to a DevOps and machine learning talk, so I'm very proud of you all. My name's Damian Brady. I'm a cloud advocate at Microsoft. You may have seen a picture of my head on my boss Donovan Brown's keynote, one of the slides towards the end. So I'm part of the DevOps team, the DevOps advocacy team at Microsoft. So that's kind of my core area, is DevOps. But lately I've been delving into machine learning a bit, and it's a really interesting field, this crossover between DevOps and machine learning. And part of the reason it's so interesting is that it's really immature. So I just want to get an idea of who's here. Who here does machine learning, AI kind of stuff right now? Okay, a little less than half. Who works in organizations that have a decent DevOps process or some kind of DevOps working? And that's almost everybody. Okay. So that's where I was coming from. I'd done a ton of DevOps both at Microsoft and in previous companies at Octopus Deploy, and then before that in consulting, I did a whole lot of consulting around DevOps too. And when I first kind of looked at machine learning and all of this artificial intelligence stuff, it was decades ago when I was at university, and it was just so inaccessible at that time. So I remember the first time I ever saw any kind of computer intelligence stuff, I was, before I went to a university, I was at a university looking around to see what courses I might want to do, and there were PhD students and master's students and so on. And I went into a room in the computer science department, and there was a guy there who was doing his thesis on neural networks, which we'll learn about in a sec. Basically machine learning. And he had built this demo that he wanted to show off. It was really cool, he said. And so he opened a page on his machine, and there were all of these little dots kind of just scattered around the screen. And then he pressed a button, and the dots kind of nicely ordered themselves into a circle so they were evenly spaced. And then he turned to me with an excited look on his face. And I was like, wow. And he explained that he wasn't telling those dots where to go, he was just giving them basic rules, and there was this emergent behavior which was kind of like the machine thinking for itself. And yeah, he was so excited about it, and I thought, wow, this is really not very cool at all. Like, this is not this far from Skynet, right? We are not anywhere near, so I kind of lost interest. The next time I saw it, which was actually when I got interested in it, was ironically when I was at that university doing my thesis. Not on machine learning or anything like that. I was doing something boring about Bluetooth and sales offsite and things when Bluetooth was new. But a colleague of mine, or somebody who was doing the same course, they were doing their thesis on neural networks. And he had entered his machine learned model into a football tipping competition. Now, the Australians would know what that is. For everybody else, a footy tipping competition is basically where you and a whole bunch of your mates get together and you put some money in a pool at the start of the football season, and every week you bet who's going to win each game, and then at the end of the season, the person who got the most right gets most of that money. So it's, you know, just friendly gambling between friends. So he trained a model to learn who was going to win these games, and he entered it into a footy tipping competition and won, not by a small amount. He crushed everyone. And so, of course, I just finished the same course as him, and I thought, well, this is a fantastic way to never have to work again. I'm going to ask him what's involved. And I said, so how hard is this? And he goes, it's really easy. You just need to build like an n-dimensional graph, and there's a bit of maths in it. How's your multi-dimensional calculus? It wasn't good. So I abandoned that idea like any good computer scientist, and went and wrote Visual Basic for the government for a few years, which is actually true. That's what I did, forms over data stuff. So the point is, all of this was so inaccessible to me back at that time. When I started working at Microsoft, I have the advantage of working with some really smart people who were able to put it in terms that I understand. As well as that, the field has increased to the point where it's completely public. Like, anybody can start using cognitive services, or even use things like custom vision, where they train their own models based on the work that Microsoft researchers have done, so that you're using transfer learning, taking advantage of all this work that we've done to build your own custom models. It's suddenly really accessible. Like, you don't need to know multi-dimensional calculus. And because it's so accessible, so there's that side of it. The other side is we're collecting a ton of data, and you need data to train these models. So because we've got so much data and the computing power has improved, it's not more accessible to everybody. So because of this, it's in more and more applications. And more companies are starting to invest in some kind of machine learning, some kind of artificial intelligence. But the problem is, unlike software development, which has been around for a long time, machine learning and the data scientists who do this work are still at this point where they're building these models and emailing them around and having a folder with zip files in it with, final model underscore new underscore latest, and 30 models there. This is the state of the art with machine learning and DevOps. So what better opportunity is there to come in from a DevOps perspective and start talking about how we can improve that process of machine learning, whether you're doing it yourself or whether other people in your organization are doing it and you need to work with them as well. So I saw a bunch of people said that they work with DevOps, but not everybody. And I saw a whole lot of people say that they did some machine learning, but again, not everyone. So I thought I'd start just with a little bit of a disclaimer. This is DevOps machine learning, so yes, it is a bit maximum buzzword, all right? I'm not going to push these things too much. We're going to do a shallow visit of what machine learning is and a bit of a shallow visit of what DevOps is, and then we're going to look at what machine learning can benefit from a DevOps perspective. So let's start by looking at what machine learning is. So machine learning, you've probably heard artificial intelligence bandied around a few times, and machine learning as well. There's a bit of a grey area about which is which. So if you can think of artificial intelligence as this broad field of computers doing things that previously required a human. And if you think about that and go back in time, that means a calculator was once artificial intelligence, because calculators used to be people who did the math. But then computers came along, and this was this artificial intelligence that could do this work. And obviously it's progressed from there. We can recognize things in images. We can do all that kind of stuff. But artificial intelligence is this broad field of anything that a computer can do that seems a bit magic. Machine learning is usually how you would do that kind of work. So the joke is, and Matt Veloso, who works for Microsoft, I believe, tweeted this, so it was really, really popular. He basically said, if it's written in Python, it's machine learning. If it's written in PowerPoint, it's artificial intelligence. AI is what you do when you're selling it. Machine learning is what you do when you're actually doing it most of the time. So this is a bit of a gray area. Machine learning is the practice of actually doing this stuff. And then inside that, we have deep learning and neural networks and things like that, which are the deeper machine learning techniques and so on. I don't want to go into that too much, but what I do want to do is explain how machine learning works, basically at a high level. This really helped me learn what it was, and this is a description given to me by a colleague, Seth Juarez. So when we think about how we write code as programmers, we would think of what the problem is, and we would come up with an algorithm. Data goes in, gets combined with that algorithm, and at the end we get an answer. So we are writing that algorithm. We know how to define those if statements and the loops and things like that. We provide that logic. With machine learning, it's good for problems where we don't quite know how the programming would work. So things like, is there a cat in this picture? Well, I don't know where I'm going to put all the if statements, right, to tell whether there's a cat in this image. I just don't know. But there is almost certainly a pattern. Like, we can see the image and tell there's a cat in it. Of course, there's a way of determining it. So how do you do that? And this is where machine learning comes in. And really, it's just switching this around. You provide a whole lot of answers and a whole lot of data and say, these are the labeled images that say whether there's a cat in the picture or not. And you let the computer work out what the patterns actually are in that data and give you the algorithm at the end. Now, what generally happens inside this blue box, you can think of it as kind of glorified guessing, right? It just has a stab at a whole bunch of numbers. It looks at bits of the picture. It increases weights of certain parts. It looks at comparisons between things. And then it does it over and over and over and over again until it starts seeing that it's getting better. And it will keep training until it's suddenly coming up with a decent set of numbers and tensors and things like that internally to give you an algorithm that actually describes that data. And that's really all it is. In machine learning terms, that algorithm is generally called a model. But the great thing about this is you can now feed this back into your application. So this model can now be the algorithm that you use in your application to feed in new data and get predictions out the other end. Now notice this is predictions, not answers, right? This is the best guess given the model that has been created based on the data that you gave it. Now that part, based on the data that you gave it, is really, really important. In machine learning, if you provide biased data, you are going to get a biased model. Your model is not racist, but if your data is, then your model will be. Like it propagates the biases that your data has in it already. So at last night's little party, there was the fun talks, and I joked about a couple of industries that did that. And for example, there was a cloud provider who looked at using machine learning to do a first pass of all of the candidates for jobs that were applying, but they used their existing workforce as the data to train whether people were appropriate or not. And their existing workforce was very white male heavy. So when you submitted an application, if you were a black woman, you would immediately get scored low. The machine doesn't have that impression. It's just the data you fed it has that impression. Biased data gives a biased model. So it's really important to have this data in there. And we'll talk about that in terms of the process itself and how machine learning works. When you look at actually that pipeline of how you get from the data all the way through to training and then into production for a predictive model, what happens if that data changes and when you need to retrain your models, when you see these biases creeping in and things like that. All right, so that's machine learning. This is the part that the data scientists do, and generally this is the only part that they know how to do. Feeding all of this into a product that is used by your customers in their website or in an app or something like that, that is beyond the data science part. That's beyond the machine learning experts part, and so that's really where they stay. And we want to expand that to be the whole software delivery cycle. So this is where DevOps comes in. DevOps itself, if you saw the keynote this morning from Donovan, he highlighted this quite well, where it's the combination of developers and operations and frankly everything else which is required to get an idea into production and make sure that it is delivering value in production. Traditionally, you think about developers and operations as these two sides of the coin. Developers trying to work fast to deliver innovative changes and bug fixes and new features and things, and operations trying to maintain reliability and stability, and quite often these are at cross purposes. As Donovan said this morning, you're incentivizing your developers to change things as fast as possible, and you're incentivizing your operations staff to stop change from happening because that breaks things. Right? DevOps is all about these teams working together to actually deliver value in the form of new features reliably and safely. So the definition that we use at Microsoft, which is Donovan's definition, is that DevOps is the union of people, process, and products to enable continuous delivery of value to your end users. Now, the important parts of this, it's people, process, and products. Nobody should be telling you that if you buy a particular product, and I'm speaking for Microsoft here as well, if you buy our product, it's going to help, sure, but it is not a silver bullet. It's not going to solve your problem. If people aren't bought into this idea and the process is not there internally, the product is not going to solve your problems. So it's really a people issue and a process issue as well. The other part which I like talking about is the fact that this is delivery of value. Right? Not delivery of features or bug fixes or new infrastructure or anything like that. It's delivery of a value. And the only way you know whether something is valuable is if you actually measure it in production. From a machine learning and AI kind of perspective, the easiest way I can think to demonstrate this is by thinking about predictive models for recommendation engines. So if you go to Amazon or something like that and you buy some products, and then underneath that it will say, here's some predictions of what you should also buy, or people usually bought these together. Now that may not be using any actual machine learning, that's probably just some correlations between groups and things like that, but that kind of work is a prime example for where a DevOps process that continually improves that predictive model can come in really handy. You can test those models, you can build a new one, you can roll it out to a small subset of people, so almost like A/B testing or canary deployments and things like that. Roll it out to a subset and see whether they click on those links more often than the people in production. If so, then roll that out automatically. And all of this stuff is things that we do in DevOps already. You know, rolling out to a canary environment, making sure that there's no problems, rolling out further if it's successful. A/B testing is really common as well. We wrap things in feature flags. You know, we make sure that our expectations of whether we've delivered value have actually delivered value by testing it in production. Now, with a predictive model, that can be handy in a lot of cases, especially with these recommendation engines. Try a new model, see if it actually delivers value, and if it does, roll it out to production. So this is where DevOps can really help. Teams that do DevOps well, this is from a report that I always refer to from DORA called the State of DevOps report. This is the 2018 edition. Teams that are really good at DevOps, the high-performing DevOps teams, deploy 46 times more frequently than low-performing teams. The lead time for changes is 2,500 times faster. In other words, the time it takes from making a change to your product, whatever it is, and getting that into production is 2,500 times faster than low performers. And then, contrary to a lot of companies' popular belief, the faster you move, the more safe your deployments actually are as well. So even though you're moving faster, the changes you make are 7 times less likely to fail because you've practiced this. Even when they do fail, you're 2,500 times faster at recovering from that failure. So all of this stuff gives a better process that enables you to deliver value faster and more safely to your customers. Now, one of the other things from this report which I find really interesting is this actually translates to business success, regardless of the industry. So this is all about software delivery, yes, but if you look at the companies that do DevOps well, they actually meet more of their own goals than companies that don't do DevOps well. Their own predictions about how well they're going to do in their industry are driven by good DevOps practices, which is really awesome. I strongly suggest that you read this. It's a very digestible report as well. State of DevOps report from 2018. All right. So let's think about the process that we use with DevOps. In DevOps, we do some planning, there's some development and testing, we do some releases to test environments and staging and production and things like that, and then we deploy to production, and then once it's in production, we don't stop there, we need to monitor what's happening in production and learn from that, feed that back into the work that we're doing. So this is something that we've been doing in software development in one form or another for a long, long time. This doesn't tend to happen in the machine learning world. In machine learning, you'll tend to get data scientists who will sit there and they'll do their work individually. They'll prepare their data, they'll get it from some data source. Maybe they'll just pull a subset from a production database, work with that. Build some models, try a few different ways of handling that data, some feature selection, things like that. And then they'll evaluate it, usually locally, to make sure it's actually performing pretty well. And then they package it up, if you're lucky, and throw it over the wall to somebody who needs to deploy it somehow. This is if you're lucky. Sometimes the data scientists will say, we've got a model I think works, can you give us the data and we'll run it through and then we'll just give you some answers. That obviously doesn't translate to embedding this model into an app, but in some cases that's what happens. So this, if you've been in the DevOps world, looks remarkably similar to the old way of deploying software, right? You do your work locally, you package it up in your development teams, and you throw it over the wall to operations and somebody else deals with it. There's certainly not this cycle of evaluation, continuous delivery, and working together in a team. And that's the state of where machine learning is at the moment. All right. So the question really is, how do we improve this for your organizations that are using machine learning? Part of the problem is that data scientists don't really care about source control. They don't care about continuous integration, continuous delivery, that kind of stuff. So number one, the problem is making them care. Number two is making this easy and not tearing them away from the tools that they're already using. So I spoke to some people people at Microsoft in a few other teams about how they try to get people to do machine learning using Microsoft technologies. And this is a while ago before some of the Azure machine learning stuff that I'll talk about later. And they said, well, the first thing is that we need to get the data scientists to stop using Jupyter notebooks and start using Visual Studio. I went, you've already lost. There's no way they are going to do that. The data scientists, they have their tools. They're scientists, right? They have their tools. They have their ways of working. If you tell them that the way we're going to improve this process is to completely tear everything out from under you and make you use different tools you're not familiar with, maybe even different programming languages. Here, learn Git, right? It took me 5 years to learn Git effectively, right? Data scientists are not developers. They're not programmers. So they need to still be able to use their own tools, which means that the people who are experts in DevOps need to often drive this kind of these pipelines that we're building. One way of doing that is using the tools that we use for software development. So when I've been focusing on this, when I've been doing demos and things like that, the DevOps tool that I use is our own. It's Azure DevOps. And you do not have to use Azure DevOps. You can use whatever DevOps tooling or products that you currently use. I'm not telling you that this is the only way to do machine learning DevOps, right? But this is actually a good way of starting. So this product was built around the idea of making your DevOps process easy. Everything from an idea all the way through to production. So boards for planning, Azure repos for keeping source control, Azure pipelines for your continuous integration, continuous delivery, artifacts for the products that you actually build, the artifacts you build, and then Azure test plans for your testing and things like that. So rather than talk specifically about how to do this machine learning stuff in Azure DevOps, I thought I'd just use these as headings. Right? These are the 5 areas that we have decided are important for a good DevOps process. Planning, source control, CI/CD, artifact management, and testing. So let's just use those as a heading, and we'll look at some of the practices that DevOps implements and how that can help you with your machine learning efforts. All right, so let's start with planning. So planning is often a difficult thing with machine learning because there is usually one goal, and that goal is to create a predictive model that does a good job, right? How do you break that down into individual tasks? Like with programming, you can look at a feature you need to implement and say that this needs a list page, it needs an edit page, it needs some back-end stuff, it needs a database stored procedure, it needs all of this stuff, and you can break it into individual tasks. With machine learning, it's quite often about experimentation. So you may just try some stuff. It might take you an hour to experiment with something, try it, realize that's not going to work, we'll tweak it a little bit. So how do you plan that? This whole process to get a model out might be one thing that lasts for 3 months, getting an actual model out. What I would say is that this experimentation shouldn't exclude planning. That shouldn't mean, well, we're just going to experiment on this for a few months until we get something we like. You should create those tasks or those bits of work as experiments that you can repeat. So in software development, we say this feature is done. We create the feature and then we deploy it to production and it's done. We've moved from here to here. It's one thing that's complete. In machine learning, you might do the same tasks over and over again. The task might be, let's try some basic regression first, right, using the data from this particular database. So what I do then is I will do a task for filtering the data for feature selection that's appropriate for that, a task for actually running some training on a subset of that data, evaluating, doing some scoring, and another task on maybe deploying that if it's good enough to a test environment where we can run some more tests. You start working on those, push them across your board, and then the ultimate outcome might be that this is absolutely not going to work. Regression is not a great way of solving this problem, but that's okay. Let's create some new tasks for the next way of doing the work. Now you might think, well, what's the advantage of that? Number one, your team knows what you're doing, right? You don't have to have these tasks that go all the way across the board and that means they're in production, right? You can have a task to say, this is what I'm working on. I'm working on feature selection in this particular database. I'm doing that work now. I'm moving it across to the done pile. When I've done that, I'm going to do some training. I'm going to move that across to the done. I'm going to do some scoring. I'm going to move that across. It's not really going to work. Okay, let's try a different technique. But it means that you're sharing this information with the other people in your team, and there's that traceability. If something actually gets to production, you can see, well, we had these other experiments that didn't work, but the experiment that did work was when we did this particular technique, we did this work, it went through, and now we've got a deployment that's gone to production, and it's very successful. You get that traceability and explainability of what happened, which is really important for a whole team, right? I would recommend as well doing this tracking in the same tool as the developers if that machine learning work is implemented in the applications that your developers are using. So if your developers are writing an iOS app and there's an ML part of that iOS app, even if the cadence is completely different, that's okay. as long as the teams are using that same tool. So the developers can say, well, what are the data scientists doing right now? Oh, okay, they're trying some of these other experiments because the last few haven't worked. The data scientists can look at that board and say, oh, it looks like the developers are about halfway to the feature set that they want for this particular sprint. Maybe we should cut our losses at this particular point, which was okay. And so let's start deploying that through to production. So you're actually starting to work as a team rather than completely isolated teams that don't talk to each other. So using that same tool means that the visibility is there. And again, your explainability of what happened is really important too. We tried this technique, it didn't work. We tried this technique, it led to a successful model that's now in production. So the planning needs to involve this machine learning. None of this, we're just going to do some experiments until we come up with a model and then here's the model that's going to work now. Right? Actually having that planning as part of your work is really important. All right, any questions about planning just before I move on from this? Cool, that was actually just a sneaky way of having a drink, making it seem like I might, anyway. Right, let's move on from planning and let's talk about source control. This by far is my #1 recommendation is use source control, right? And having data scientists and saying, right, we just need to use Git now. Here's how Git clone works. And then all of these complicated ways of saying, well, it's actually just a hash of the change set and this is how it works and we can do pull requests and stuff like that. Data scientists they're not programmers, they're not going to work that way. So having tooling that helps them work that way is really important. Thankfully, the tooling is there in almost everything that data scientists use now. You can do source control in Jupyter Notebooks. Visual Studio Code is starting to become the default IDE or default editor, I suppose, for people doing anything, really. And that integrates really nicely with Git. So everything should be in source control. Try to make it as easy as possible for your data scientists to get on board with that. Don't drop them to the command line to do Git commits. It's not going to work. You might notice as well that I have an asterisk there, everything in source control. I mentioned a few times that data is extremely important for this training, and that may mean petabytes of data that you have. Don't put petabytes of data in your Git repository, all right? There are other ways of having a canonical data source where you can say, this is where my data lives. If it's too big to actually do your training on it, we do an extract every month into a smaller database, which is a representative sample of what's in production. We clean it, and that is our canonical data source for training. Right? Having this stuff documented and explained to say, this is where the data lives, and when we did our training for this particular model, this is what the data looked like. That can be a hard problem as well. How do you do a snapshot of 100 petabytes of data? Well, you can't, right? I guarantee there'll be organizations out there who say, well, we write tools that can do that silver bullet for you. We can just snapshot petabytes of data and it just works. I would recommend you find out exactly how that works before you hand over any money, because that's not an easy thing to do, right? There are some techniques that you can implement if you do need to do this stuff that enable you to snapshot data or to actually get versions of data that are traceable back into history. Things like write-only data, so having a timestamp field, which is when that record expired, and only writing a new record to say this is the replacement of what was already there. If you have that timestamp, you can go back in time if you need to and say, give me all of the data that hadn't expired at this particular point and was, so the data at a particular point in time, if you need to. Right. The other thing you can do is actually just do semi-regular backups and say, look, every week we do a backup or an extract into a particular database, and that's what we use for our training that week. Document that very, very carefully to say, this model that we trained was based on this particular subset of data, archive that at a particular point, create a new one and start training off that data. It's going to depend a lot on the scenario that you have. If it's predictive or recommendations engines, you probably don't even care what the data looked like 6 months ago when you trained that model because it's irrelevant now. Like the recommendations engine should be built off what data you're using right now, not what data there was 6 months ago, because things change. Right? So you may not want to do it at all, but you do need to define what that canonical data source looks like. In terms of the code that you actually have in there, all of your ETL stuff or ELT stuff, so extract, translate, and load, and those kind of things. Basically just taking the data, filtering it however you need to filter it, and then ending up with the things that you're going to use to train on. That stuff should all be in code. It shouldn't be somebody running some queries and copying data and putting it somewhere else like that. That should be in code so you can run it automatically every single time you go through the pipeline. The other thing which is a really handy idea from DevOps is the idea of infrastructure as code. So in software development, we tend to talk about that as this is what our production system looks like, and we have that defined in code using whatever we use. ARM templates, we might use Terraform, we might use something else like that, but that's really defining the environment that our application is going to run in. And yes, that is absolutely important. But in data science and in machine learning, you might want to actually define the training environment as well. You don't want a situation where a week's worth of training that just takes a very long time can only be run on Dave's machine over there because he has the right version of Python and the libraries that you've got as well. And in fact, he ran it on this machine that had 3 GPUs, but we can't do that anywhere else because he's the only one with these GPUs and so on. So defining what that infrastructure for the training looks like is really handy too. And this is a technique that we tend to use in the Azure machine learning world, where you have these learning environments, these data science virtual machines that you can define up front and say, I want a virtual machine that looks like this, that is this shape and this size. I'm going to do my training on that. So it's defined, and every single time you run your training, you're going to end up with a consistent model based on the training that you've done in that environment. And that's really, really important. You definitely don't want the I could only train this on one person's machine, we're never going to be able to recreate that model again situation. So defining the training environment in code is really handy too. And of course, that code should be in source control. Now, if you do this stuff, that means at any point, you can start building a pipeline where everything that you care about is in code, right? You can automatically run these pipelines. You can build new models, and you can end up with these artifacts right at the end of it. So that brings us to the CI/CD part. In software development, we tend to talk about build and deploy. Build, test, deploy, things like that. Build is quite similar to train in a machine learning environment. Like the artifact we get out of it is a predictive model. Testing is quite often called scoring or evaluation or however you want to do it. But you're basically testing the model that you've created to make sure it's okay. But you can do some testing before that. So things like linting. Does your code actually look all right? Like, have we got some decent functions that are named appropriately? We're not using single characters for variables. All of the stuff that we do in software development to improve the teamwork or improve the communication between your teams. All of that kind of stuff can be part of that pipeline. Running your tests, doing the linting, evaluating your models, and then scoring them to see how they perform. That stuff can be part of your pipeline. The training and the experiment runs as well should be part of that pipeline. So yes, pull the source code, run all of that sort of stuff, build up the infrastructure if you need it to do your training, and then kick off the training and your experiments and things like that. All of that should be part of the pipeline. The model management should be part of your pipeline. When you have trained a model, where do we store that model? How do we version it? I'll talk about that a little bit more in the artifacts section, but that should be part of the pipeline as well. We have this artifact, let's put it somewhere and say, this is the version of the artifact. It came from this code, from this data, on this date. Here's the scoring, here's all of our evaluation, and this is what it looks like. And then the part that when people start talking about ML ops or machine learning operations or DevOps for machine learning, they quite often just jump straight to operationalization. In other words, we've trained this model, how do we actually get it into production? And so they might wrap it in a Docker container and then push it out to production. Then that's fine, but if that Docker container came from a model that was trained on Dave's machine over there because he has three GPUs, it's not repeatable. It's not a process that you can run when Dave is away, right? It's a process that needs to be automated the same way that we automate continuous integration and continuous delivery. So operationalizing, taking that model and putting it into a format or into a package type that can be used for the application that needs to use it. Docker seems to be the de facto that I've seen for, especially for web applications. Wrap your pickle file or whatever it is in a Docker container and just expose an endpoint so that whatever your application does, it can just hit that endpoint inside an Azure container instance, or maybe a Docker machine that you have running, or a Docker instance that you have running, or maybe a Kubernetes cluster as well if you need to scale out. That's a great way of actually operationalizing your model. Or you might want to package it into a core ML thing so you can build it into your iOS application. But that process should all be automatic. You should end up with a model that can be used in an application. The other part of CI/CD that we talk about is the triggers for these pipelines. So it's really easy, especially with software development, to trigger a new build or a new training exercise or a new experiment and then a new deployment based on changes to code. But it's straightforward to do commit triggered ones. So every single time there's a change to the code, maybe we're changing the algorithm we're using, maybe we're changing some libraries that we're using in our TensorFlow code. When we commit and push that, we can kick off a pipeline, we can build a new model, we can deploy that out to production. That's fine. But that's not the only place that you might want to commit, you might want to trigger a new build. You might want to trigger a new training exercise based on data staleness. So if your data is 3 weeks old, your model's probably not going to be performing that well, or maybe it's irrelevant with 3-week-old data. You need to trigger a new deployment. So either time-based ones, or even data-based deployments, or data-based triggers. So when the data, you could put some metrics around it. When the data drifts by a certain amount, that's a trigger to create a new model, even if it's based on exactly the same algorithms and exactly the same stuff that you used before. Triggering that, building a model, operationalizing it, and putting it into production without anybody having to do any actual work at that point can be really powerful. That's a hard problem, and you really need to know what your organization needs for this stuff. So what the model is for, and how you determine whether it needs to be retrained or not. Yeah, we'll get into some data-driven stuff a little bit more later. So this is the CI/CD stuff, and this is where the DevOps really comes into power. For the people who are doing machine learning at the moment, I want to know whether this is something that you're looking at thinking, well, that would be nice, but I don't think it's possible with what we're using at the moment. Is everybody who put their hand up for the machine learning stuff, when you look at this kind of pipeline stuff, are you thinking, yes, this is something we can automate? I just want to see some hands. Yeah, okay. That looks about roughly the same number of people who said they were doing machine learning stuff. So this stuff can really greatly improve your life if you do it properly. Any questions about the CI/CD stuff? Because this is where the guts of the DevOps practices can really have advantages. All right, it's becoming increasingly obvious that I'm just doing that so I can get a drink. Let's look at the testing stuff, or the monitoring and learning stuff. So you need a retraining strategy. It's not enough to deploy your model, have it in production, and say, well, that's great. We can go on to a completely different piece of work now. Can you imagine if a recommendations engine did that? Like, you would start getting for one thing, you would stop getting recommendations for anything new, right? Because the data is not there. It's not going to recommend stuff that's new, that it doesn't know about. It's not going to be able to work effectively like that. Retraining as well on data drift or on success drift as well can be really handy for things like, if we think about the canonical example of, is this a hot dog or a pizza or something, any of those images where or any of those examples where you need to define what's in an image, right? If those images start changing over time, which happens, right? Then you need to be able to retrain that model in an efficient way based on what's actually happening in production. An example I heard about the other day where there was an organization using some form identification. So they would just scan a bunch of forms that people had sent in, and they would run them through this machine learning thing just to identify what the form was. Because there were maybe 3 or 4 forms that they kept getting from people. So they just scan them all into images and then run it through an algorithm which would say, this looks like a loan application. This looks like a default notice. This looks like, whatever it is. And they could sort it into the piles. It was a really simple application. And then they got a new scanner, and it stopped being able to do this work. Like, it stopped having any success with this. The brightness was off, or the the paper went in at a different angle, or there was a different margin for some of them, or maybe the form itself changed, or maybe people started using blue pens, right? If you don't have a way of identifying that this stuff is happening, you're just going to end up with a model that keeps failing, right? So monitoring in software development is really important to know when you're getting bugs, when there are exceptions, when your application's not performing. You need that kind of monitoring in your machine learning as well to identify when that model is not having the success that you need it to have and trigger some automatic retraining, or at least identify that something needs to happen. Right? So you need this retraining strategy. You need to know when to retrain and how to retrain. This builds into this data triggers that I mentioned before for CI/CD. So if there's data drift, if you start having less success than you were before, at what point do you automatically trigger a rebuild to see if that's going to fix the problem? That's probably the easiest way to do it. If the data's changed, just retrain the model, push that out, see if that works before anybody needs to have any intervention. Performance is an interesting one as well. It's all very well to have a really, really accurate model, but if it takes 4 or 5 seconds every single time somebody uploads an image, that's not very useful. And remember, DevOps is about delivering value continuously. It might be accurate, but is it valuable if people get too sick of it and don't use it anymore? Well, of course not. So sometimes you might need to trade off accuracy for performance. Or you may need to know that your performance is getting worse. Maybe the pool of data that your model is pulling from after it's been in production for a while for its predictions is now suddenly just a bit too big and it's not performing very well. You need to be able to retrain. And again, you need the monitoring around this to be able to tell. And this is something we do with software development. We monitor what's happening in production, but quite often it doesn't happen in machine learning. Portability is an interesting one as well. So the idea of having a model that you can move around or that you can scale up and scale down. And this is kind of why Docker has become one of the de facto ways of operationalizing your model. If you have a model that runs in a Docker container and performance starts suffering, and you know that because you have monitoring around it, then maybe you can just scale up. If it's just a simple endpoint that's going to detect or going to look at an image and determine what it is, or provide a recommendation, maybe you can just scale up that Kubernetes cluster. And being able to have a portable model where you can move it where you need to is really important as well. So a model that only runs on one particular machine is really expensive to scale up. It's back to the days that we used to have an operations team take weeks to provision a new virtual machine for an application, right? So having a portable model can mean that it's really easy to scale up and down, and it means that your monitoring can even be automated to say when the performance suffers, let's just scale it up a bit. So the monitoring and learning is really an important part of it as well. So let's look at all of these things in the in terms of a process itself. So this is kind of a software development process, right? Where we have our application developer, they write their code in whatever tool they usually use, in an IDE like Visual Studio Code or Visual Studio or whatever it is. They write that code, they push it to a Git repository. Azure pipelines might pick that up and then deploy it to Kubernetes or deploy it to an application or something like that. This is the way we tend to work, and there's a pipeline that automatically happens to do all of that stuff. So let's introduce a machine learning team where that ML model needs to be part of this application. So now we have a data scientist who does some data preparation with the databases or their canonical data source. They use whatever tools they normally use. Jupyter Notebooks, they might use RStudio, they might use something like that, or Visual Studio Code. That code also goes into the Git repository alongside the application code. Maybe it's a different repository if they really want to be careful about it. I don't see any purpose of putting it in a different repository. But maybe whichever way they go, it's going to be in a Git repository. They may also want to run some training locally. It can be expensive to push things and have it running on your data science virtual machines that have 25 GPUs and cost $1,000 a minute in the cloud, right? Maybe you just want to run some training stuff locally. So yes, you can automatically train and test some models. And you may even be able to pull the infrastructure as code, so the definition of what that training machine needs to look like, maybe just in terms of what versions of Python, what versions of TensorFlow, things like that you're using. So pull that stuff from source control and run some tests locally, make sure all of that works. Yes, that's fine, let's push some code back up to Git. So you can run your training locally, you don't have to do it as part of your pipeline. But then once it gets to Git, once you've pushed a version of your code and say, right, this is code that we want to work. Code that we want to train on. Azure pipelines or whatever DevOps tool you use can pick up that code, build the application from the application source code, train the models from the machine learning code, and again, using that infrastructure as code to define what that training machine should look like. And then at the end, deploy all of this stuff to an environment like Kubernetes or Docker or even an application by combining that stuff all in one pipeline. And then you can start getting your inferencing in your applications itself. So you can see the pipeline doesn't actually look that different. It's the same stuff. It's just we're doing it with machine learning now, and we're not separating these teams. We're not throwing stuff over the wall. It's all part of this same process. So I want to show you, recently there was a conference called Velocity, and there was a team from the Azure machine learning team at Microsoft who had been working on the Azure Machine Learning Service, which I'll show you in a second. And they wanted to show off an actual pipeline doing some work, but using a tool called Kubeflow. The ML people may know what that is, but it's basically a pipelining tool or a tool for running experimentation and doing some training and scoring and things like that. So they wanted to use Kubeflow, but they also wanted to use Azure DevOps. So I helped them build this pipeline. They did a lot of it themselves, and then I changed some processes and helped them with the work that was happening. So the way this works, this is a real pipeline that they've used. They're using one of those sample applications which just determines whether an image is a taco or a burrito, which is the kind of stuff that we really like doing as cloud advocates. So this is their build process, right? The first thing they do is they define a number of containers, or they build new images for the containers that are going to run the training. So this is your infrastructure as a code. You can change the definition of what these containers look like, and it will build new images and get those ready for Kubeflow to actually do the training in. So this is the first task. We do a lot of stuff with Azure CLI just to build these Docker containers. And then we basically create these images. And then we just trigger Kubeflow and say, here's our code, here's our training scripts, these are the images, the infrastructure you're going to use to actually do the training. Once that happens, our build is done. We've triggered that stuff, Kubeflow is going to do its work, and at some point it's going to register a new model with Azure Machine Learning Service. That model creation will now trigger a release in Azure DevOps, in Azure Pipelines. So we have a release process that's triggered on the new model being created. And that process goes to through a couple of stages. The first thing we do is we run some profiling on that model to make sure it actually performs okay and give us an idea of what kind of infrastructure we need to run this model. We can put in some tests there to make sure that it's not going to cost too much money. We can make sure that it runs on the infrastructure that we care about, and just do that profiling to make sure that works. So this actually does some deployments to Azure Container Instances and does some testing. And then we deploy the model to an ACI instance, Azure Container Instances one. So we deploy it, we test that deployment actually works. So we run it with some test data to make sure we haven't broken the model completely. And if that works, we have these post-deployment gates to query some monitoring to make sure that our performance hasn't gone down, to make sure that we haven't just climbed in the terms of exceptions, we're not hammering CPUs. So we have these monitors on our test environment to make sure that we're okay to go to production. So this is a feature of Azure Pipelines called Gates, which is basically like an automated way of somebody looking at it saying, yes, this looks okay. But you can do it in an automated way. So this is what we do. We deploy it to ACI, we test that it passes our smoke test, it's giving the right responses for our test data, and then we make sure that we haven't broken anything from a performance perspective. Once that happens, we can deploy to an AKS cluster. So this is our production environment. And it's This one is currently waiting for approval. So we have a pre-deployment approval process where somebody actually has to tick the button to say, yes, I'm going to approve that deployment, and then it will just go out to our Kubernetes cluster. Let's look at a previous release where we actually did that approval and what happened there. So we approved it. Let's see who actually approved it. David approved it, probably on stage. And then our job basically just did a model deployment using the Azure CLI, the Azure Command Line Interface. And so it called the Azure Machine Learning Service and said, here is our model. Build it into a Docker container, deploy it to this AKS cluster. And now we're in production. So what does this look like in Azure? Well, in Azure, we have this machine learning service. Let me just zoom in a tiny bit. We've called this Kubeflow AML. And it has a number of things which basically help manage the different parts of your machine learning process. We have the experiments, so you can track the experiments you've actually run. And this is going to load. So we can see we've done a bunch of these experiments. Let me just close this so we've got some more room. And when we did them. And we can look at some details about that as well, I think. So we can have a look at that experiment. We can see when it was prepared, how long it ran for, and all of that kind of stuff. There's the idea of pipelines, which I think needs a bit more maturity, but it's basically an orchestrator that lives inside Azure Machine Learning Service as well. I would still, because I'm used to the DevOps tool being Azure DevOps, I still lean towards that. The compute is our definitions of what these compute environments look like, and we have a Kubernetes cluster that we run our stuff on, but we can also train on this Kubernetes cluster if we want. So these are our compute environments. We have the models that have actually been created, and when we create a new model, this kicks off our release process, and when we register that model, we can have a look at what that model looks like. We can download it, we can get a link directly, we can create a Docker image from it. So this is actually, I think this is a TensorFlow. I think we're using TensorFlow as well. You can also deploy from this as well. We have our images, so the things we've built from those models, and then we have our deployments. So we can see that we've deployed that food deploy AKS to an AKS cluster, and there's our deployments to the ACI cluster, ACI environment as well, Azure Container Instance environment. Activities, I don't know a lot about. They're still working on this. So this is all public, but I believe it's public preview still at the moment. So you can use this. It's really useful for actually managing that, and you get that traceability all the way through. So what does this actually look like? Well, let's just hit that endpoint. So this is the cluster that we've deployed to in production. Oh, I can't move in anymore. So let's just grab a picture of a taco. What's a good one? There you go. Let's grab that. Copy that image. And then back in Postman. And again, we're just hitting an endpoint here. This is where we deployed to. We're providing this data. This is all running inside a Docker image. Did I copy that? Nope. Copy image. Oh, wait. Right, that's not going to work. Copy image link. Let's paste that in. And have a look at the response. We can see that it said its tacos at 97%. So this is just a Docker endpoint that we've hit. But creating that thing running in production was completely automated. Somebody changed, in this case they just changed a README file, but they might have changed the model code that they were using. It created a build which did some training, did some scoring, made sure everything was okay, and then that triggered, they registered a new model from that. That triggered a deployment process which did some profiling to make sure that we hadn't done anything bad in terms of performance. It deployed to an Azure Container Instance, so a test environment where we ran some tests using known images just to make sure that it's actually performing okay. And then we looked at our monitoring to make sure that that hadn't decreased performance by too much and we weren't getting exceptions. And when that was okay, we waited for a manager approval, clicked the approve button, and it went out to production to an AKS cluster. All of that happened automatically with the exception of clicking that approve button because we've built this DevOps process into our machine learning service. And you can imagine we might have a parallel one for our application, or maybe we build the application alongside this model at the same time, and deploy a new version of our website that uses that version of the model as well. So this stuff, it's still a relatively new area. in machine learning. But it's really, really important to start building these good practices into our data science process so that we're not making the same mistakes that we were making in software development 10, 20 years ago, or in some cases, last week. Right? We can use these learnings and improve everything. Some resources from things that I've run through as well. The Azure Machine Learning Service is really cool. Go and have a look at that. It makes a lot of the stuff that you're doing in your data science process, your machine learning process, really handy. All of those things from experiments and models and data science virtual machines, the compute engines and things like that, really handy. You can get a free Azure account as well if you just want to try this. So free trials and limited use for certain things as well if you just want to try it. There's a link for that. The command line interface was basically how we were doing this. We were registering a model with the CLI for Azure. So there's an extension for the Azure command line interface that talks to Azure Machine Learning. That's available there as well. And then there was also a session by David, the guy you saw who approved that one, at Build recently, where he talks in a fair bit of depth about what the Azure Machine Learning Service does itself. So that's a pretty useful one if you want to delve into the detail of that in a big way as well. All right. So hopefully that gave you a bit of a picture of what can be done, and especially the people in DevOps. This should be your job if you're in an environment that is starting to use machine learning. Apply the good principles that we've got in DevOps to this machine learning process so you can work together with the data scientists and not make the mistakes that we made in software development for so many years. Thank you everyone very much for your time, and I will be here answering questions for the next little while. Thank you.